Gravitational field lines and equipotential surfaces. A field is a region where objects with a certain property experience a force. We can represent fields with lines. You'll be familiar with magnetic field lines, showing the direction a compass needle will point, something like this. So wherever we placed a compass, it would point in the direction of the line as shown, coming out of the North Pole and into the South Pole. The field is strongest at the poles, as can be seen from the lines being more closely packed together at this point. A gravitational field is a region where objects with mass experience a force. The force is always attractive, and the field lines show the direction of the force. The density of the lines, as with the magnets, indicates the strength of the field. The field due to a point source, or due to a sphere, like that of the Earth, is shown by radial field lines. So the Earth would have a gravitational field represented something like this. The lines are further apart as we move out. Here, for instance, they're further apart than here, and this shows that the gravitational field of the Earth weakens as we move away from it. Field lines can never cross, as this would mean a force in two different directions at that point. As we raise an object up above the Earth's surface, it gains gravitational potential energy. We can say that at a particular height, an object will have a certain amount of potential energy per unit mass being a kilogram. We call this the potential at that point. So this is a property of a particular region in space, regardless as to whether a mass is there or not. This potential depends only on the height above the Earth, so all points at a particular height will have equal potential. We can link all points of equal potential to give what's called an equipotential surface. This is effectively a spherical shell around the Earth. Satellites travel around equipotential surfaces. As their potential energy does not change, no work needs to be done to keep them moving. So here again we have the gravitational field lines around the Earth, and we could add this ring, which is an equipotential surface. In 3 dimensions, this would make a spherical shell around the Earth. Notice that the field lines are always perpendicular, or at right angles, to the equipotentials at every point here. We say that the potential in space is 0. The potential reduces as you come closer to the Earth, in the same way that the potential energy of a falling ball is reducing. Therefore, the potential close to the Earth must be negative if it is to be less than 0. The potential at the Earth's surface is around minus 62 megajoules per kilogram. This means you would need to give a 1 kilogram mass 62 million joules of energy to make it escape from the Earth's gravitational field. Here again we have the gravitational field lines around the Earth. These lines would of course continue to infinity, getting further and further apart. I've shortened them here for clarity. You remember the potential at the Earth's surface was minus 62 megajoules per kilogram, so we can draw an equipotential surface just above the Earth's surface at a value of minus 60 megajoules per kilogram. Further out, we would have an equipotential surface with a value of minus 50 megajoules per kilogram. Further out still, minus 40 megajoules per kilogram, minus 30 megajoules per kilogram, and so on. You notice that as the field weakens, we need a larger distance to give the same change in potential.